So in this video, I will just briefly talk about the notion of Brauer groups. So to understand Brauer group, first we need to know what's a central simple algebra. I will not go into details of any of those things. You can find them in any standard book like the one I've been following for some time now. It's called I don't remember the name of the book, but its author is Benson Fall and Keith Dennis. That's one of them. And another book that I've been following recently, it's by J.P. Seth on local fields. You can find Brauer Group in I think one of the latest chapter, but Seth doesn't cover a lot of theory in Brauer Groups. And there's another book which is by Philip Gill. It's on central simple algebra and Galois. Yeah. So this book is pretty nice. It covers a lot of theories of both Brauer groups, its connection to Galois cohomology and a lot of stuff. Also some algebraic geometry is there in the last book. Yeah. But Benselfer is the easiest one and the most basic one. So yeah. So anyway, so what's the central simple algebra? It's so take a field K and let's say you know what's an algebra, so I'm assuming you know what's an algebra. So A is central simple algebra over K if as a ring its center is isomorphic to K and uh, it has no two-sided. It has no, of course, non-trivial two-sided idea. So an algebra is just a module which is also a ring such that the module structure and the ring structures are compatible between themselves. And in fact, we'll be mostly talking about finite dimensional simple algebras. Finite dimensional means because A is a vector space over K, as I just said, because it's a module over K, meaning a vector space over K. So as a vector space, its dimension is finite. So we'll be mostly talking about finite dimensional surface. And one prime example, and the easiest example is over any field K, you look at the matrix algebra on for any M. That's one easy example for central simple algebra. And now how to show its central simple? The first thing is you can show that the center of matrix algebra consists of all the scalar matrices. So clearly this is isomorphic to K. And secondly, any two-sided ideal of M and R, where R is any commutative ring, not necessarily a field. It's a general statement. Any commutative ring with unity is of the form M and I for an ideal I of R. It's a commutative ring, so any ideal is a two-sided ring. So, in the view of uh, this proposition or this statement, you see that um, is simple because K is a field, so it has no ideal. So it's simple. It's a central simple. And another example, let's call it example zero because it's really the most basic example that one can have. You can talk about it's called a quaternion. what's that? So you start with the field key of characteristic other than 2, we'll see why, and it's denoted by say AB, and it's denoted by two elements x and y. So that x square is A, y square is B, and xy is minus. So the AB's are just two non-zero elements of K. In particular, I think most of you have seen the case where A and B both are minus 1. That's called the usual Hamiltonian algebra. So the convention is to write it as generated by two elements I comma j, where I square is minus 1, j square is also minus 1, and ij is minus j. But sometimes we also write ij to be another variable key. So that's standard Hamiltonian. And you can show that it's also a central simple algebra. And its dimension is 4. You can easily check because it's generated by literally 1, x, y, and xy. So its dimension over k is 4. For matrix algebra also it's obvious, its dimension over k is n square. So one similarity from these two examples is that dimension is always square of an integer or a square of a natural number. It's 4 here, it's n square there. In fact, that's a general statement. So let me just write the statement without going into the proof. Proof is actually not very difficult. So, uh, any central simple algebra over K has dimension n square for some. This n is called as the so is the degree of central simple algebra A. Degree of A over K. So we take the square root of the dimension and we call this as a degree. That's one thing. And there are some standard theorems regarding central simple algebras. So one thing is, let's start with the easiest one, at least the easiest one to state. Let's call it Skolem method. Says that any automorphism of a central simple algebra is in fact an inner automorphism. So inner automorphism means it's of the form, if phi is an automorphism from automorphism of A, central simple algebra over field K, then it's of the form like for some y, the usual inner automorphism. So that's one step. And in fact, this also shows that automorphism of M and K can be shown to be uh, isomorphic to the projective general linear, right? For obvious reasons, because you take the short exact sequence by taking an element of GL in K, and you send the map where x going to that element of GL in K times x times that element in. And this map is surjective, the last map, because any automorphism is of this form. by this column method. And in a scalar matrix, we'll go to the identity. Right? So it's and the projective this thing is just means GLNK modulo set. So that's one statement. This theorem is actually pretty good. And now let's come back to the notion of Brauer groups. So the basic thing is Brauer group basically classifies all those finite dimensional centers up to some isomorphism. The main thing is Brauer group classifies centrism. That's the main thing. And what does it mean? It means that say you have a field key and you take two central circle algebras of finite dimension. If A and B are two central circle algebras with key of finite dimension, then see there are two ways to look about it. One thing is the easiest way is by looking at the Wetterman structure. It says that A is isomorphic to matrix algebra over some division algebra. So it's B is also isomorphic to matrix algebra over some division algebra. Right? D prime division algebra or division algebra. Division algebra. Right? And now we define A and B are same if and only these two division algebras are isomorphic. So by this way, we're defining an equivalence relation on all the central superalgebras over K. And this is easy to check that itself with equivalence relation. And equivalently, one can also check that this equivalence relation is same as saying that there exists uh, m positive integer such that you take A tensor uh, m and k the isomorphic to B tensor m m. You can also check like that. So if you have two integers, positive integers, such that after tensoring it with those two matrix algebras, if the both the sides are isomorphic, then one can say that A or B is same. So these two things are actually equivalent. So in this way, we are getting an equivalence relation, and in this way, we are getting another equivalence relation. So we say A and B are same, or in other words, Brar equivalent. It's not difficult to check that these two uh, identifications are actually same by using the structure theorem and some isomorphism, which are not, but these are really easy to check. Basic non-commutative. And thus, yeah, so this is how we are defining a set basically. So for a field key, we are actually defining all these equivalence classes, right? And now we want to show that this forms a group under some operation. So to find this operation, one can check that a tensor product makes this a group, well defined. That means what? That if you have one element, one class of central simple algebra, you take another class of central simple algebra, You define it to be the first tensor, then that becomes another central simple algebra. That's easy to check. Tensor product of two central simple algebras are again central simple. And you take that thing. So this makes a well-defined group. And in fact, it's an abelian group because tensor product you can do either A tensor B or you can do B tensor A. Both of them are isomorphic. Brauer group of K is an abelian. Right. And so whenever you have a group, you need to have an identity element, and it's easy to check that the class of matrix algebra uh, is is the identity. That's why I was saying that these are the most basic central super algebras there can be because these are really the identity. It doesn't change any other central super upon tensor identity. And for any A or any class of equivalence class of CSA, you take its opposite algebra. This class is the inverse. And what does it mean? It means that you take A, tensor it with A of means just the ring multiplication operation is reversed. It means in A of you define the multiplication as x some circle dot is just y. This is the operation in A of. That's it. Nothing else. And you can check that this is equivalent to matrix algebra, meaning that A of serves as the inverse of. So these are some of the fundamental things. And one also says that there's another version of Brauer, it's called the relative Brauer. Let's take a look at that before closing the video. Relative Brauer. This means what? You take two field extension, finite field extensions. And you define this as the kernel of this map A going to A tensor. So this means what? You are taking all the center separate algebras over small t, and you are extending the scale. So you are changing the base to make it an algebra over a bigger field, capital. And if this after tensoring, if this thing becomes isomorphic to or becomes Brauer equivalent to symmetric algebra, then you say it's an element of the relative group. And in fact, one can show that the absolute Brauer group, sometimes this thing is called absolute Brauer group. This thing is basically, look at this, take union of all Galois extension, finite Galois extension. This is sometimes, in fact, in the book of Sayre, I think he defines Brauer group of K by means of the relative group. So this is the definition of Sayre, I think, but one can show by the other definition as well that this is the thing. And to show this, it's there's a theorem. I don't remember the name. I think it's by Noether, and I think it's by Coether and Noether that uh, any central simple algebra admits a separable splitting field. And separable means the usual definition in the field theory, but this splitting field is a bit different. So let me define. So field K is said to split a central simple algebra A if A tensor K with the isomorphic to matrix. This is what you mean. And you can show that among all those splitting fields, there is at least one of them which is separable. And now it becomes easy because then any separable field you can look at its normal closure to make it into a, say, a Galois extension. So you can always find a splitting field that's Galois. So by this thing, one can show that this Brauer group of K is indeed union of all such things. And this relation also shows another interesting thing, which is let me again just state it as a lemma info because this is not very difficult. That any Brauer group is torsion. Torsion meaning every element has finite order. And in fact, one can show it using this thing that you look at the relative Brauer. These things, in fact, uh, isomorphic to as a group. You look at say, and by the way, this K over K is a Galois extension, as I said. So once you have a Galois extension, you can talk about this Galois cohomology. I'm not going into details of these things, obviously, but the thing is, one can show that in this way that this is the second Galois cohomology of the Galois group of K over K, like this, K, the units of the larger field. And because this group is torsion now, this is easy. This is just property of the group cohomologies by the way the cohomology groups are defined. One can easily check that. In fact, this is true for any n that if you have any this thing or where m is any g module, whatever that means, and g is a finite group, then this thing becomes zero. So every element, order of every element, uh, or is at most order of the Galois group in this case, which is a finite group because we are taking all the finite Galois. So each of these relative Bragg groups are torsion, and you are taking the union over all such Galois extensions. So the absolute Bragg is also torsion. So this is one. And now talking about examples, the thing is most of the basic examples is as you can expect that if K is algebraically closed, the Bragg group is trivial for K algebraically closed. This is easy to see because there is no division algebra over any algebraically closed uh, field. In fact, another thing, there is something called quasi-algebraically closed or pseudo-algebraically. So for those fields also the Brauer groups are zero. Okay, I think it's also called C1 field, and this also includes all the finite. So all of these things the Brauer groups are zero, or I mean trivial. First non-trivial example is the Brauer group of the field of reals, and this is actually isomorphic to Z mod. This is due to the Frobenius theorem. What does it say? It says that uh, there are no central simple algebras over R except uh, the quaternion algebras. So let me write this. What's the Frobenius theorem? I will undo this thing. So it says that if there is a division algebra over R, then or division algebra say with R as the center because it's a we are talking about central simple algebra, then it's a finite dimension. Let's take as well. Then D is either the field of reals or the field of complex or the Hamilton, the usual. And now because we're talking about central simple algebra, so in particular overall the only finite dimensional central simple algebras are are handable. I mean up to that Brauer equivalence. Because C is not central because its center is the entire grid. This is so it was because of this theorem the Brauer group of R is a two elements. And one can show that H tensor H of is indeed or H tensor H is indeed a matrix algebra. Is isomorphic to M2 of C, or you can show that it's isomorphic to say M4 of R. That means that H is its own inverse. So H is an element of order 2. That means it's two element group. It's Z mod 2. So that's one of the example. And there's another example, which is the Brauer group of periodic numbers. This is Q mod Z, and I think I should stop. So these are some of the basic things of Brauer groups that I've been studying for some time. And I think the book by Philip Gill and I think there's another author, Thomas Zanelli. I think this book is pretty good. It also says when a Brauer algebra or when a central super algebra is split. For example, for a generalized quaternion algebra or a quaternion algebra, this thing, one can show that if one can associate a conic with any such AB. And if you show that there is a k rational point, that means you have a conic, some conic, let's call it C. If you have a point on the conic, that means that the algebra is split. That means it's isomorphic to the matrix algebra over here. And in fact, more generally, also talks about some properties of group cohomology, as well as there's another class of algebra, central simple algebras called the cyclic algebras. I think this book is pretty good for basic understanding of Brauer groups with this connection to algebraic geometry. Or in fact, it also deals with some K theory, like some K1 of some central simple algebra. There's also some number theory. Brauer groups. There is so by the way, yeah, there's another thing that Brauer group of rings because see we have been only talking about Brauer groups over a field. So one can also talk about Brauer groups over a ring, and that is important because of number theory perspective. Because often we talk about number fields. So for that, that means the finite extensions of Q. It's a number field. So one can talk about Brauer groups of the number fields as well. So I think this book by Philip Gill is pretty nice in this regard, because he also talks about those things.